Section: Introduction. In this section, we introduce Proximal Policy Optimization, PPO, a popular actor-critic algorithm based on the policy gradient approach. PPO enhances the stability of policy learning by optimizing a modified objective that limits the difference between the new and old policies during training. The objective involves the current and old policy models, sampled questions, and output sequences, with a specific token in the output. A clipping hyperparameter is used to stabilize updates, and the advantage at each step is typically estimated using Generalized Advantage Estimation, GAI. This objective encourages the new policy to improve while keeping changes within a safe range. Next, we discuss Group Relative Policy Optimization, GRPO, which we proposed in DeepSeek Math. GRPO removes the value function and estimates the advantage by normalizing rewards among a group of responses for the same prompt. For a given prompt with multiple responses and their rewards, the group normalized advantage is calculated. This normalization helps maintain the reliability of the gradient signal, especially in situations with sparse rewards. Instead of using a KL penalty in the reward, GRPO directly adds the KL divergence between the trained policy and a reference policy to the loss. We also present Decoupled Clip and Dynamic Sampling Policy Optimization, DAPO, a recent reinforcement learning method aimed at addressing challenges in large language model, LLM, reasoning. For each question with a correct answer, DAPO samples outputs from the old policy, calculates their rewards, and maximizes a specific surrogate objective. DAPO separates the upper and lower clipping limits to enhance exploration, filters out samples where all responses are either correct or incorrect, aggregates losses at the token level, and applies special reward shaping for overly long or truncated responses. We then outline various reinforcement learning techniques that help stabilize optimization, reduce variance, and speed up convergence in LLM reasoning tasks. We categorize these techniques as follows. 1. Baseline design. Baselines are essential for minimizing variance in policy gradient estimation. Recent approaches suggest using the mean reward within each group as the baseline and calculating it for each sample based on the average gradient from other samples in the group. 2. Clipping strategies. Clipping helps control excessive updates in policy optimization and can be applied to rewards, advantages, or ratios. The clip ratio higher method relaxes the upper limit in PPO's ratio clipping to enhance exploration. 3. Normalization strategies. Normalizing rewards or advantages stabilizes gradient magnitudes. Common methods include batch-level and group-level reward normalization, as well as reward shifting without standard deviation to avoid bias. 4. Filtering strategies. We filter out uninformative or undesirable samples before computing gradients. This includes removing overly long responses, filtering overly incorrect or trivially correct samples, and excluding samples outside a targeted difficulty range. 5. Loss aggregation granularity. The way we aggregate loss affects how much each token contributes to the overall objective. We can compute per token advantages to reduce length bias or aggregate losses at the sequence level. 6. Additional loss functions. Auxiliary losses can support the main objective and regularize training. KL loss constrains divergence from a reference policy, while SFT loss incorporates supervised fine-tuning objectives. 7. Reward design. Shaping the reward function can guide the desired output characteristics. Examples include length penalty to discourage long outputs, formatting reward to encourage preferred structures, and length-dependent accuracy reward that combines correctness with output length. In this work, we focus on 4 key aspects: normalization, clipping, masking, and loss aggregation, and we conduct detailed analyses of their mechanisms and practical applications. Section Summary. In this section, we discuss various reinforcement learning techniques for optimizing large language models, including Proximal Policy Optimization, PPO, for stable policy learning, Group Relative Policy Optimization, GRPO, for reward normalization, and decoupled clip and dynamic sampling policy optimization, DAPO, for enhanced exploration. We also categorize strategies such as baseline design, clipping, normalization, filtering, loss aggregation, and reward design, emphasizing their roles in improving model performance in reasoning tasks. Section: Training Algorithm. In this section, we utilize the open-sourced role framework, which is designed for efficient reinforcement learning optimization in large language models, LLMs, to conduct our experiments. We employ the PPO loss, using advantage values calculated with the reinforce algorithm as our basic reinforcement learning baseline. To align with previous research, we set the rollout batch size to 38 and sample 39 responses for each prompt, with a maximum response length of 40 tokens. Our learning rate is set to 41. For text generation, we use a top_p value of 42, a top_k value of 43, and a temperature of 42. To evaluate reinforcement learning techniques across different model sizes, we test two models, Qwen 3-4b and Qwen 3-8b. Each model size includes both non-aligned pre-trained versions and aligned versions, allowing us to assess the benefits of reinforcement learning from various starting points. For our training datasets, we exclusively use open-source datasets like simple RL-Zoo data and DeepMath to ensure reproducibility and fairness. We randomly sample from these datasets while removing a large number of examples with simple, true, or false labels, as we find that models can produce correct answers through faulty reasoning, which can introduce noise into the training process. We visualize the difficulty of the training dataset using GPT-4o. For easy data, we randomly sample 44 entries from simple RL-Zoo data easy, which includes problems from GSM 8K and Math 500 Level 1. For medium data, we select the 44 easiest examples from the Deep Math 103K dataset based on difficulty annotations. For hard data, we randomly sample 44 entries from DEEP-MATH 103K, with the sampling probability based on each entry's difficulty level. All our experiments are conducted on 6 math datasets, including Math 500, Olympiad Bench, Minerva Math, and subsets of standardized tests like AMY 24-25 and AMC 23. These datasets cover a wide range of complexity, from basic arithmetic to advanced competition-level mathematics, allowing us to thoroughly evaluate reasoning capabilities. We investigate how data difficulty affects the training dynamics of the Qwen 3 models. We analyze training convergence patterns through loss dynamics, accuracy trajectories, and generalization gaps across 3 complexity levels: easy, medium, and hard. Our results show that as training epochs increase, the model displays different accuracy patterns depending on the difficulty of the training sets. When faced with harder samples, the model tends to generate more tokens to fit complex reasoning patterns. Comparing the unaligned base model and the aligned model under the same conditions, we find that aligned models start with significantly higher accuracy and produce longer responses early in training. However, the performance gain from additional training steps for the aligned model is modest, with only about a 54-point increase in accuracy, indicating that the current RL4 LLM algorithm provides slight improvements for already optimized aligned models. Advantage normalization is a common technique used to reduce gradient variance and stabilize policy optimization in reinforcement learning training for language models. However, there are notable differences in its implementation. For instance, GRPO and RLOO use group-level normalization, which calculates advantages relative to other responses within the same prompt to encourage competition. In contrast, Reinforce++ uses batch-level normalization, arguing that optimizing within a single prompt too much can lead to reward hacking and hinder generalization, especially when response diversity is low. To evaluate the impact of advantage normalization on PPO variance with a value function using the Monte Carlo return target, we conduct experiments under a unified training framework, exploring 3 settings: no normalization, batch-level normalization, and group-level normalization. We focus on the Quen 3 base series models due to their low initial scores and high potential for improvement, ensuring a fair comparison by minimizing confounding factors. We assess small, 4B, and medium-sized, 8B, models to see how normalization techniques interact with model capacity. Our findings indicate that both normalization techniques significantly affect the model's convergence speed, stability, and final performance. Specifically, group-level normalization consistently leads to more stable training dynamics and better final performance compared to batch-level normalization and no normalization. Batch-level normalization is sensitive to reward distribution skew, often resulting in performance collapse when a few outlier samples dominate the advantage estimates. However, when we adjusted the reward mechanism to a larger scale, batch-level normalization showed significant improvement in policy learning. This demonstrates the sensitivity of the advantage normalization technique to the reward mechanism. Section Summary. In this section, we describe our use of the role framework for reinforcement learning optimization in large language models, LLMs, employing PPO loss with reinforce for baseline comparisons, and we detail our training datasets and evaluation benchmarks across varying problem difficulties. We also analyze the impact of advantage normalization techniques on training dynamics, revealing that group-level normalization yields more stable performance compared to batch-level normalization, particularly under skewed reward distributions. Section: Impact of the standard deviation term in advantage normalization. In this section, we examine the impact of the standard deviation term on advantage normalization. We previously noted that different normalization techniques are sensitive to the reward scale, prompting us to explore the reasons behind this. We believe that variations in reward scales affect the standard deviation calculation, which in turn influences normalization strength. Specifically, when model responses yield very similar rewards, like when they are mostly correct or incorrect, the standard deviation becomes very small. This small value can lead to excessive amplification of gradient updates during normalization, causing the model to focus too much on very difficult tasks, a situation we refer to as difficulty bias. To investigate whether the standard deviation calculation is the main factor affecting normalization performance, we used a batch-level calculation method, which had shown unstable results earlier, to compute the mean of advantage and conducted experiments focusing on the standard deviation term. We tracked accuracy after training on both simple and difficult datasets. The results for easy data showed that the policy quickly converged to consistent behaviors, resulting in a tight distribution of reward values. Consequently, the standard deviation of this distribution dropped significantly. When we applied standard deviation-based normalization in this scenario, the small denominator led to an excessive amplification of reward and advantage values, causing large gradients that destabilize training and could even result in gradient explosions. These findings support our hypothesis that the standard deviation term is crucial for advantage normalization. To reinforce our conclusion, we compared results from a hard dataset, where we found that the standard deviation of rewards remained relatively high during training. In this case, both mean-only normalization and standard deviation-based normalization performed similarly well, keeping training stable regardless of the normalization method used. Thus, the choice of normalization style had minimal impact on convergence or overall performance in this smoother reward distribution. In summary, our experiments indicate that when reward distributions are tightly concentrated, excluding the standard deviation from advantage normalization can prevent abnormal gradient amplification, enhancing model training stability. However, for tasks with higher reward variance, either normalization method is generally adequate for maintaining stable optimization. Next, we highlight the importance of the standard deviation in the effectiveness of advantage normalization and seek a more robust combination of mean and standard deviation for reward shaping. We employed a stable group-level mean calculation method, combined with two approaches for computing the standard deviation: local, group level, and global, batch level. Our evaluations across different model sizes showed that the global level calculation provided a clear advantage. We believe this is because the batch-level standard deviation offers stronger normalization by effectively reducing gradient magnitudes, preventing excessive policy updates. This method aligns better with the biased reward signals often found in sparse rewards and coarse-grained advantage fitting, leading to more stable learning. We also address the challenges posed by the clip mechanism in LLM-based text generation. While it improves PPO training stability, it can suppress low-probability tokens, leading to entropy collapse, where strategies become deterministic and lack diversity. This creates a negative feedback loop that hinders performance on complex reasoning tasks. To counter this, we introduce the clip-higher mechanism, which sets a higher upper bound for advantage, allowing low-probability tokens more room for improvement and expanding exploration in those areas. Through extensive experiments, we find that the effectiveness of the advantage clip technique varies across different model architectures. We tested both non-aligned, base, and aligned, instruct, models to summarize usage guidelines for clip-higher. Our results indicate that the impact of increasing the upper clipping bound is model-dependent. For base models, adjusting the upper clipping value has minimal effects on policy entropy and can even harm performance compared to the standard policy. In contrast, aligned models respond differently. Raising the upper clipping bound significantly slows entropy collapse and improves downstream evaluation metrics. This difference arises because base models operate with a low policy clipping rate, limiting their exploration capabilities and hindering the discovery of high reward paths. Therefore, a higher clipping upper bound yields little improvement in learning dynamics. Conversely, aligned models, which benefit from advanced pre-training or post-training techniques, show better reasoning and generalization. For these models, a higher clipping upper bound helps bridge the probability gap between tokens, alleviating entropy collapse and facilitating more diverse action sampling during training. This mechanism maintains higher entropy while increasing the likelihood of finding optimal solutions, as demonstrated by improved evaluation metrics. Section Summary. In this section, we investigate the impact of the standard deviation in advantage normalization, finding that a small standard deviation can lead to excessive gradient amplification and instability during training. Our experiments reveal that using a global standard deviation calculation enhances normalization effectiveness, particularly in scenarios with sparse rewards, while the clip-higher mechanism helps mitigate entropy collapse in model training by allowing for greater exploration of low-probability tokens. Section: Analyzing the effectiveness of clip-higher from a linguistic perspective. In this section, we analyze the effectiveness of clip-higher from a linguistic standpoint. Building on our earlier demonstration of clip-higher's behavior, we now examine how it influences reasoning logic through token-level linguistics. We find that setting a strict upper limit on token probabilities imposes tight constraints on policy updates, particularly affecting connective tokens like therefore, if, and, but. These tokens are crucial for guiding reasoning in dialogues but often exceed clipping thresholds, leading to their suppression during optimization. While this clipping stabilizes the overall token distribution, it may hinder the model's ability to generate diverse argumentative structures. When we raise the upper limit, we see a significant increase in the flexibility of policy updates, allowing for greater deviations in token probabilities. Under these relaxed conditions, the frequency of clipped tokens decreases, shifting the focus from discourse connectives to common functional tokens like is and the. This change enables the model to explore a wider range of reasoning structures and enhances response diversity, while still maintaining the stability of core sentence structures. Next, we discuss loss aggregation, which influences how each sample contributes to the overall optimization gradient. We compare token-level and sequence-level aggregation methods. The sequence-level approach used by GRPO averages losses across all tokens in a sample and then across the batch, treating each response equally regardless of length. However, this can disadvantage longer responses, reducing their learning impact. To counter this, we adopt a token-level approach that ensures each token contributes equally, regardless of response length. We systematically evaluate the effectiveness of these aggregation strategies on different models. Our findings show that token-level loss improves performance for base models, enhancing convergence and accuracy, especially on difficult datasets. However, for aligned models, sequence-level aggregation often performs better, as these models already exhibit strong reasoning capabilities. Thus, we conclude that the best loss aggregation strategy depends on the model type. Token level is ideal for base models, while sequence level is preferable for instruction-tuned models. Lastly, we address the issue of overlong filtering during training. A fixed maximum generation length can truncate complex reasoning processes, leading to incomplete answers being misclassified as negative samples. This can contaminate the training signal and reduce learning efficiency. To mitigate this, we introduce overlong filtering, which masks the reward signal for excessively long responses. We aim to analyze how this technique impacts performance across various datasets and identify the best scenarios for its application. Section Summary. In this section, we analyze the linguistic effectiveness of clip higher, revealing that stricter clipping limits hinder the model's ability to generate diverse reasoning by suppressing connective tokens, while relaxing these limits allows for greater flexibility and exploration of discourse structures. We also compare loss aggregation strategies, finding that token-level aggregation benefits base models, whereas sequence-level aggregation is more effective for aligned models, and we address the challenges of overlong filtering in training, emphasizing the need for careful threshold management. Section: When to use the overlong filtering. In this section, we explore when to use overlong filtering. While recent studies have shown the advantages of this technique for policy training, the effects of varying maximum lengths remain unclear. To investigate this, we utilize the Quen 3-8b base and Quen 3-8b as our initial policy to compare how different maximum generation lengths influence training dynamics. Our findings reveal that when the filter threshold is set to 102 tokens, we see significant benefits from overlong filtering. However, increasing the threshold to 104 tokens leads to a noticeable decline in these benefits. Upon analyzing response lengths, we notice a pattern. With a threshold of 20,000 tokens, models using overlong filtering tend to produce longer responses compared to the standard policy. In contrast, a shorter threshold of 8,000 tokens results in shorter responses. We further examine the distribution of filtered responses that exceed the maximum length. In the 20,000 token setting, both correct and incorrect samples are filtered more often due to repetitive or non-terminating outputs, which indicates unproductive generation. This suggests that higher length limits allow overlong filtering to effectively remove less useful samples that do not aid model learning. As we continue with reinforcement learning training on models fine-tuned with instructions, we observe an increase in the proportion of samples that are repetitive and unable to terminate normally. This points to a decline in the model's ability to accurately identify end-of-sequence tokens, leading to issues like output redundancy. After implementing the overlong filtering mechanism, we see a significant reduction in these abnormal samples during training. This change indicates that the model becomes better at distinguishing between completed and truncated generation samples, thus avoiding invalid learning from incomplete outputs. Additionally, this mechanism enhances the model's ability to accurately model termination behaviors, allowing it to disregard unfinished samples instead of incorrectly treating them as negative examples. Next, we introduce a simple combination called light PPO. Based on our detailed analysis and empirical evaluations, we identify two key guidelines for non-aligned models. For smaller models, such as 4B base and 8B base, advantage normalization can significantly enhance performance by transforming sparse rewards into more reliable signals through group-level mean and batch-level standard deviation calculations. Token-level loss aggregation also proves to be an effective technique for non-aligned models, particularly for base model architectures. We propose that the combination of advantage normalization and token-level loss aggregation should lead to substantial improvements in policy optimization. To test this, we integrate both techniques into non-aligned models using the vanilla PPO loss without a critic, resulting in light PPO. Our results show that light PPO outperforms the more complex DAPO algorithm, which includes various advanced techniques. Specifically, light PPO demonstrates a consistent upward trend in performance for smaller models, while other policies quickly decline after peaking. This advantage is largely due to the normalization technique, which mitigates the issues caused by uniform reward distributions in datasets with varying difficulty levels. We also evaluate light PPO on larger base models. Our findings indicate that when training 8B base models with long-tail generation capabilities on challenging datasets, light PPO continues to excel. This improvement arises from eliminating overlong filtering, which typically limits smaller models' ability to generate complex outputs, and shifting to token-level loss aggregation, which proves more efficient for base models.